Okay, folks, let's get started. Uh, we have around uh, half of the class. So, today we are going to begin chapter number 4. And, okay, just we are using Zoom after a very long time, so there may be some small problems. I don't know why these green lines appear on the screen. Okay, uh, so this is chapter number 4 from your textbook by R.C. Hibber, and the title of the force chapter is Force System Resultant. Um, let's move forward. There can be a better name for this chapter, but that's what we have. Let me see how can I get rid of these green lines. Mm, we should use result. Okay,
सर ये किसी लड़के ने लगाई है वो ही रिमूव कर सकते हैं ओके।
okay, okay. आप लोग अपने आप को म्यूट कर दें। वैसे तो मैंने सेटिंग में किया हुआ था, लेकिन कुछ लोग जब ज्वाइन करते हैं तो वो शायद अनम्यूट होते हैं। ओके, हाँ, आप लोग यू कैन अनम्यूट योरसेल्फ इन केस यू हैव अ क्वेश्चन और यू हैव अ प्रॉब्लम, सो यू कैन अनम्यूट एंड यू कैन आस्क, otherwise just keep yourself muted. Okay, so here the first slide is about movement of a force. Uh, you have learned about movement mm, in your high school physics, and the movement is basically the rotational effect of a force. Like when we open or close a door, we apply a force, and the result of the force is rotation. So basically, you are applying a force, but the result of the force is rotation. So that effect is called movement. Some people would call it torque, but we will call it movement. People in physics mostly call it torque, but in civil engineering, we commonly use the term movement. You can see the definition. Let me read it for you. Tendency of a force to rotate the body about point that is not on the line of action of the force is called the moment of a force, or simply a moment. I see that uh, here is our force. See, here is our force, and I have marked here the line of action of the force. Now, the force is producing movement about this point O, and you can see that the point O is not on the line of action of the force. Okay. A force cannot produce movement about any point which is on the line on its line of action. So the point will always be off the line of action. Okay, line of action. And the movement is actually not about point O. It is about the axis which is passing through point O, which is Z axis. Okay. And just for simplification, we say movement about point O, but it is actually about the axis which is passing through point O. And the magnitude is very easy to find. Simply multiply the magnitude of this force with the perpendicular distance d. And you see right here, the angle is 90 degree. 90 degree and 90 degree for the distance with respect to the point for which you want to determine the moment, and that is point. Okay, so the magnitude of the moment is directly proportional to the magnitude of the force. Means if you increase the force, the movement will increase, and it also depends directly proportional to the perpendicular distance or moment arm called d. Means if you increase F or if you increase D, in both cases, the moment will increase. And this bottom line, as I said before, movement is always about an axis. Here, the movement is about z axis. Okay, but you will see that commonly we will say movement about a point. That is just a simple way of saying it. Okay, and you can see that here you see this blue circle right here. You can see this, and this is uh, counterclockwise. Okay, so movement always be designated as clockwise or counterclockwise, and this one is clockwise, counterclockwise, and that is very easy to imagine um, with respect to the direction of the force. You see, let me clear this down. Okay, you see that this direction, this direction right here will tell that what is the um, sense of the movement, clockwise or counterclockwise. If I reverse this direction, if I make this direction like this, then the movement will be clockwise. Okay, I think, yeah. So again, I would, before moving to the next slide, just see that this angle is 90 degree. Okay, now look at the next slide. In the next slide, you will see that, let me move to the next slide, just a minute. Mhm. I, I cannot move to the next slide. That's the reason. Okay, just yes, mhm, yes. Now I can move. Okay, now I have to clear the screen. Let me see how can I clear the screen. Okay, clear the screen with these marks. Mhm. Can't figure out how to clear the screen, but okay, no problem. I can for now just use the eraser. Okay, so the difference in this figure and the previous figure is that previously the load and the moment arm were perpendicular to each other. And in this case, you see here that look at this angle. This angle is theta, okay, which is not 90 degrees. So it means that we cannot multiply this F with this D to get the moment because the D always has to be perpendicular distance with respect to the line of action of the force. This is the line of action of the force. It means now we have to multiply F with something else, and that something else, that some other distance must be perpendicular to the line of action. And here you see this distance right here is perpendicular distance. Okay, it means now our movement arm is not D, but by using, you see, a triangle here, you see, by using this triangle, this right angle triangle, we can get the perpendicular distance. And now our perpendicular distance is d sine of theta. Okay, so always remember that we, to calculate the moment, we must multiply the force with the perpendicular distance. Okay, And if the perpendicular distance is not directly given, you have to find out the perpendicular distance by using the angles and other distances. Okay, right here what it says if the force F is applied at an angle which is not 90-degree, and then it will be more difficult to turn the bolt since the moment arm d sine of theta will be smaller than d. Okay, so when the distance or the moment arm is smaller, it means smaller movement is produced. When you apply the same force, but the moment arm is smaller, the moment produced is also smaller. It means now it has become difficult to turn this bolt. Okay. Okay. Moving forward. Next slide. Okay. This I will clean this first. Okay. Now you see another figure. You see that the force which we are applying right here, F, it's line of action. This line of action, right here. Just you see that the line of action of this force is passing through point O. Okay, or in other words, point O is on the line of action of the force. And in the first slide, we learned that the point O must be must not be on the line of action of the force. So if the point is on the line of action of the force, that force cannot produce movement about that point. And any layman can understand that the way this force is being applied, that bolt cannot be rotated. Okay, we have learned from our experience that to rotate that bolt, we must apply the force at some angle, uh, either perpendicular or at some other angle, but not like this as it is shown here. So let me read the statement. If the force applied is along the wrench, this along the wrench means along the length of the wrench, the moment arm will be zero. Okay. Since the line of action of F will intersect, line of action will intersect point O, or in other words, you can say z-axis. As a result, the moment of F about O is zero. And what is the result? No turning can occur. So you cannot open or tighten this bolt if you are applying the force like this. Okay. So force, if you want to turn it, you have to either apply it like slide number one or like slide number two. Slide number one tells you the best way. Okay, this is the most efficient way of applying the force if you want to turn this bolt. This one is not the efficient way, but still you can open the or tighten the bolt. And this one, nothing is going to happen. You cannot do anything. You are just, you will be wasting your force. Okay, I have a question in the chat. The question is there any major difference between the formula for the movement or the torque? Um, Look, in uh, in your high school, you have been calling this torque maybe, but we are calling this movement. But in engineering, you will see in mechanics of material, you will study another thing which will be called as torque. So here the movement will be different and torque will be different. Although both of them are rotational effect, but you will see that the torque will be like twisting. This is not twisting, this is turning. Okay. Like for example, if you have a wet cloth and you want to drain the water, so you hold that cloth in your two hands and you twist it. That is called torque in our language. So both movement and torque are rotational effect of the force, but they are about different axes. Okay. So yes, in engineering, torque and movement will be different. Okay, they are, different and similar at the same time, but they are not this exactly same. Okay. Okay. So, and the other question is, what will be the moment on the axis? Moment about the axis is same. Just multiply the force with the distance, perpendicular distance. When you just multiply it, then, whatever is the answer, that is your moment. Okay, now moving forward, we shall learn more about the sense of the moment. Okay, let me clear the screen. There must be a short way to clear the screen. Okay, yes, this meeting, the Zoom only allows you 40 minutes meeting. So you will see that in 10 minutes, the meeting will finish, and I will send another link to the CR, and CR will share with you, and you will join the meeting again. Okay, so let's just let's finish these 10 minutes and then move forward. Okay, now here we have the scalar formation of movement. We are trying to, as I said, that the movement may be clockwise or counterclockwise. So whenever we mention the movement, we always tell whether it is clockwise or counterclockwise. There is another way of specifying the sense of movement, and that is with the right hand. You may have studied the right hand rule. So both ways you can specify the movement. Okay, let me read this for you first. We can generalize the above discussion and consider the force F at endpoint O. You see right here, this is the force F, and this is point O. Just a minute. And this is right here, is point O, which lie in the shaded plane as shown. You see, uh, this is the shaded plane. Okay, the moment MO about point O or about an axis passing through O and perpendicular to the plane. See, we call it MO, but actually it's about the axis which is passing through O. But that's okay, we can call it MO. So movement this is a vector quantity since it has specified magnitude and direction. So the force F, which is producing movement about point O, or the axis passing about point O, is a vector quantity. And you see that this distance d is perpendicular distance right here. You see perpendicular distance with respect to O. And if you want to find its magnitude, simply multiply the force with the distance d. Okay. So this d is basically the moment arm. And we can also call it the perpendicular distance from the axis at point O, or we can simply say distance from point O. Okay, in the line of action of the force, um, from the axis of point O, sorry, to the line of action of the force. So see, to the line of action of the force, you can say to the line of action of the force, or you can simply say that the distance is from point O to the force F. Okay. Uh, so you can easily understand the units of the moment. Force, say, is Newton, and the distance is meter. So you can say, or force is kilonewton, distance is meter. You can say that the units are kilonewton meter. It can be Newton millimeter. It can be Newton meter. In FPS system, it can be pound feet, pound inch, if fit, whatever, all these. You learned this briefly in your job number 4, principle of movement. This is a 3D view, and right here is the plan view. So you can see this blue circle that tells you that force F is producing counterclockwise movement. Okay, force F is producing counterclockwise movement. Okay, and in the plan view, you can also see. Okay, right here, see, this is the plan view. You're looking from the top, and again, you can see that this is the counterclockwise movement, which is produced by the force F about point O. Okay, so this is the basic concept. So far we have learned that a force can produce movement about a point which is not on its line of action, and you can calculate that movement by multiplying the force with the perpendicular distance with respect to the point about which you want to calculate the moment. Moving forward to the next slide, slide number 7. This is the basic example of the door. We open and close the door. Uh, just a minute. Let me see if I can change the color of this. Yes, let me see if yellow is better. Okay, so you see that uh, a person right here is applying this force F and trying to open the door. And the force F, you see, is perpendicular to the door right here. Uh, mm, Better than the yellow. You see, this angle is 90 degree. And here in the other picture, the same force is applied at an angle theta. Okay, not at 90 degree. So this is an efficient way of opening the door, and this is a less efficient way. Okay, this is not a very good way. I would question mark this, that it's not a very good idea to open the door by applying the force at an angle other than 90 degree, unless there is really a strong reason. So you see here a 50 Newton force applied at 90 degree with respect to the door, and the length of the door is 0.8 meter. So the movement produced is simply 50 into 0.8, 40 Newton meter. Okay. Now the same 50 Newton force is applied at angle other than 90 degree. Okay. So if you extend the line of action of the force and try to find the perpendicular distance, you see that it is less than the previous one. It is less than 0.8. It's only 0.6. So the same 50 Newton force will now produce 15 to 0.6, 30 Newton meter, less movement. Say, so it's less efficient way. Okay, you are wasting your effort. Similarly, if you apply the force 50 Newton in line, or I would say the line of action of the force, if it is passing through the hinge of the door about which the rotation has to be created, then the moment arm is 0. Okay, and the moment produced will be 0. And any person can imagine, if you start pushing the door like this, the door is not going to open. We know about this, but this is a mathematical way of expressing that no movement is produced, no force, no movement is produced, no rotation is going to happen, and that because the line of action of the force is passing to the point about which you are trying to produce the movement. Okay, moving forward further. Okay, let me clear the screen. There should be a better way to clean the screen. I think there is, but I can't seem to figure out. Okay, um, again, about the direction. Okay, let me read it for you first. The moment MO is defined by its moment axis, which is perpendicular to the plane that contains the force F and its moment arm. Look, this plane right here, this plane contains both the force and the point O about which it is producing movement. And the moment axis right here, you see, moment axis is perpendicular to this plane. It is shown right here, right here. The moment axis is perpendicular to the plane of the force. Now, you can use the right hand rule. Right hand rule is used to establish the sense of the direction of M naught or MO. According to this rule, the natural curl of the finger of the right hand, remember it is right hand, okay, as they are drawn towards the palm. Okay, folks, I think we can restart the lecture. So, we were talking about the direction. Just a minute. We were talking about the direction. So, you see right here, the right hand. So, look, this force F is producing a counterclockwise movement about point O. Okay. So what you do is you can curl your finger of the right hand in the direction of the movement, clockwise or counterclockwise, and you will see that your thumb will tell you about positive or negative. Okay. If the thumb is directed upwards, we may call it positive. Okay. Thumb is directed downwards, we can call it negative. But this right hand rule and the thumb is mostly used. Just just give me a minute, please. Okay, so this right hand rule is mostly used to specify the direction or sense of movement, I would say, when we are uh, using or we are solving a 3D system. When we are dealing with 2D system, and we shall be mostly dealing with 2D system, we shall see that we shall only specify the direction using clockwise or counterclockwise. Okay, for example, in this case, the moment produced by the force is counterclockwise. We simply specify it like CCW. I'm sorry about the handwriting, but we will only write that the movement is counterclockwise. Or we can specify or decide a sign convention where you say, okay, we will use clockwise as positive and counterclockwise as negative. If we do that, we don't have to write clockwise or counterclockwise. We simply write positive or the negative sign. So mostly in 3D systems, we use right hand rule to decide the direction of the movement. And in the 2D systems, we will use clockwise and counterclockwise. Okay. Okay, moving forward, the next slide. Let's look at this next slide. Let me clear this first. Okay, now here you see that there are many forces. Previously, there was only one force. So here you see that we have F1, we have F2, and we have F3. And looks like we want to find out the moment about point O because of these three forces. So what do we need? We need the perpendicular distance from all the forces. Perpendicular distance D1, perpendicular distance D2, and perpendicular distance d3. So we can simply multiply f1 with d1 F2 with D2, and F3 with D3. Okay, and then we can algebraically add them, and that will give us the resultant moment about point O. And you can see this blue circle, the proportion of a circle, it tells you that F1 is producing counterclockwise movement. Okay, and is producing F2 is producing uh, clockwise movement. Okay, F3 is producing counterclockwise movement. So one of them you can call positive, the other you can call negative, and then algebraically sum them. Okay, so that's how we calculate the resultant movement. Let me read this for you. For two-dimensional problems where all the forces lie in the xy plane, see, all three forces are lying in xy plane. Okay, none of them is out of plane, so it's a 2D system. XY plane, the resultant moment MR about point O, uh, can be determined by finding the algebraic sum. So this is the underlying algebraic sum. Never miss the sign, positive or negative. Algebraic sum of the moment caused by all the forces in the system. Okay. Uh, I have a question here in the chat. It says, in this case, would M1 and M2 cancel each other? Uh, M1 and M2 are opposite to each other in the sense, but it doesn't mean that they can cancel each other. They can compensate each other a little bit, but their magnitude may be different. For example, this M1 may be 100, okay, maybe 100, and M2 may be 80. Okay, so they cannot cancel each other. Yes, only if they are exactly equal. So they will compensate each other, but not cancel each other. Okay, one of them can be positive, other one can be negative. We will see. And the other question is clockwise negative sign. We will decide later. Clockwise is negative or counterclockwise is negative. It's up to our own choice. We'll see. Actually, our objective of learning this is ultimately to analyze the structures. So when it comes to the structures, uh, I mostly use clockwise positive because in some situations counterclockwise positive may not be as efficient as clockwise positive. So I mostly use clockwise positive. But if you read the book, you might find, especially physics people, they use counterclockwise positive. But our knowledge and understanding is beyond the sign convention. Sign convention is a very small thing. You can decide any sign convention and you can solve the problem accordingly. But we will decide just one and we will stick to it. There is no benefit of switching sign conventions. So we'll see uh, about the sign convention. Is something we can decide later. Okay, or maybe a problem you will see in the next slide. Then we will follow that. Okay, moving forward. Yeah, it's the same thing as on the previous slide. Here, it is you know you see as a convention we will consider counterclockwise movement, and now this sign convention is coming from the book, and right now this expression which is written here is according to counterclockwise positive. Okay, so as sign convention we'll consider counterclockwise movement as positive since they are directed along the positive z direction. This is actually he's referring to right hand rule, that if you curl your finger like this, you curl your finger like this, and this is a plan view. You curl your finger in the counterclockwise direction, then your thumb will be directed upwards or out of the page. Okay, so or positive z direction. That's why he's considering counterclockwise positive, and clockwise is considered as negative. But remember that this is not a universal truth. It is just, a practice here. Maybe we can later on change it. But so it should not bother you clockwise positive or counterclockwise positive. Just try to understand that one is different from the other. Okay, you pick one book, it's use clockwise positive. You pick another book, it use counterclockwise positive. So just adjust yourself according to any sign convention, whatever some book is using. So here, if counterclockwise is positive, you see that the resultant moment, how we are calculating F1 D1 F1 into D1 is actually this one, which is counterclockwise. It is taken as positive. F2 D2 is clockwise and it is taken as negative, and F3 D3 is again counterclockwise, is taken as positive. So you add them algebraically, whatever is your answer, that will be the resultant moment about point O, about this point. Okay, so you can algebraically sum the moments to find out their resultants. Okay, okay. Moving forward on a small example right here. Let me clean this. Okay. So here is a small question, just a practice problem. Uh, Question is determine the moment of the force about point O. Okay. Now force is 100 Newton. Point O is right here. Okay. So what is the formula for the moment? Moment is force into the perpendicular distance. So from point O, uh, you have to find the perpendicular distance. You see this distance right here, which is at right angle to the line of action of the force. This is the line of action of the force right here. This is the line of action of the force. So the perpendicular distance is basically 2 meter. So simply multiply 100 with 2 meter, 100 with 2 meter, and you get Newton, 200 Newton meter. Simple. Okay. So 200 Newton meter is the magnitude. Now see, what is the direction? Without the direction, the answer is incomplete. Look at the direction. You have to understand the direction that the force is trying to produce this kind of movement. Like this. Okay. It is shown by this blue arrow as well. Okay. So this movement is what? This movement is clockwise. So write, you can either make a small like this to show it is clockwise, or according to your sign convention, if you have considered clockwise negative, you can just write a negative sign, minus 200. Okay. Or if you have considered clockwise positive, just write positive 200. Okay. What is important here is to understand that this force is producing clockwise movement. Some students cannot really understand that. They cannot imagine clockwise and counterclockwise, but you have to understand this. If you cannot understand whether the force is producing clockwise or counterclockwise movement, then you will always be in trouble, and you will always make mistakes of signs, and your answers will be incorrect. So make sure that you understand how this force is producing clockwise or counterclockwise direction, and that's actually coming from this arrow. This arrow will tell you that in which direction the force is trying to move, and then you sense whether it is clockwise or counterclockwise. Okay, let me discuss some other problems, and maybe if you are confused, you can get a better understanding. Next slide, right here. Okay, this is the same example from the book. Now again, look, the question statement is the same. It's the same question actually. The question, let me go back and tell you again what the question is. We have to find the moment about point O. Okay. So in every problem, you will see that there is a point O. So moving to the next slide right here. Okay. So you see right here is point O. Okay. We have to find the moment about point O because of this force 50. Okay. Now you see that the force 50 is away from the point O. But keep in mind the basic thing that you have to multiply the force with the perpendicular distance from the point. Okay. Now the force is here. So what you will do is force is here. What you will do is you will extend the line of action of the force. Extend the line of action of the force, and from point O, draw the perpendicular distance. This perpendicular, right here. So this distance is your moment arm, which you can call D. Okay. So from the point about which you want to determine the moment, you have to identify the perpendicular distance. And you see this perpendicular distance is given here, 0.75. Okay. So it may not be direct, it may not be placed right there where you need it, but it will be placed somewhere in your diagram. Okay. So you will simply multiply 50 with 0.75 and it will give you the moment. 50 into 0.75. So this is the magnitude. The next thing is the sense, whether it is clockwise or counterclockwise. And for that, again, you have to see the force is a sliding vector. You can slide it along its line of action. Okay. So the force is like this basically. Okay. And the moment arm is right here. This is the moment arm. So based on this direction, you see the the force is trying to rotate or produce movement like this. Okay. So the direction of the force is the direction of the force which will tell you what is the sense of the rotation. And this rotation is clockwise. Okay, clockwise. So you see here, he has shown a small arrow showing clockwise movement. Okay. Okay. Then let's move to the next problem. You see, the next problem is this one. You have a 600 Newton force, and again, right here is the point O, and we want to calculate the moment about point O. Same story. Extend the line of action of the force, okay, and identify the perpendicular distance to the line of action. This is the this is the perpendicular. This is the perpendicular distance, and see if this is given. If it is not directly given, you have to find out. For example, in this case, in the previous problem, it was directly given to us, 0.75 meter. But here it is not given to us. What is given to us is this inclined distance, 1 meter, okay, and this angle right here, 45 degrees. So what we can do is we can get this perpendicular distance from by making this triangle. Look at this triangle, this triangle. So this vertical of the triangle is basically our distance d. You see, it's the same thing. Both are same thing, and you can easily find that out by 1 sine of 45 degree. Okay, so sometime the distance is directly given, sometime some other distances are given, and you have to use right angle, triangle, sine, cosine, or something else, add, subtract, to figure out what is the movement arm. So right here again, you see 600 is multiply with the moment arm right here. This moment arm is this. Okay, it's just placed somewhere else, but it's the distance we need. One side, see, 600 into 1 sine of 45, and you get 424 Newton meter. Note down the unit. The force is in Newton and the distance is in meter. Okay, this is the magnitude. Now look at the direction. The direction, you see, if you extend the line of action of the force, and this is the perpendicular distance right here, what the direction is doing, what this direction is trying to do. This direction is trying to rotate like this. Okay? It's trying to rotate about point like this, whatever is this object, this object. Okay, and you can see it shown with this blue arrow as well. It is counterclockwise. Okay, it is counterclockwise like this. So you see that a counterclockwise arrow is shown here. Clear? Any question? Okay, let me explain the other ones as well. So you see that you have to do some working before you can actually find out your answer. Okay, let's do the other one. Let's do this one. Now here again, you see there is a point O and there is a force 400. We need the moment of this force about point O. Okay, fine. Moment point O is here, force is here, they are far away, but the basic principle remains the same. We need the perpendicular distance from point O to the line of action of the force. You see, the line of action of the force is this. This is the line of action of the force. And from point O, just draw an arrow, just draw a distance. This distance, and this distance is 90 degrees. So this is basically the moment arm we move. This is our D. So the basic principle never changes, that we need perpendicular distance from the point about which we want to use the uh, about which we want to determine the moment. I have a question in the chat. If we use the arrow, then we not use the sign. Yes, if you want to use this arrow, then you don't have to write positive and negative. But you will see that when we will do calculations, we will always use sign. This is because here is only one force. There is no need of adding movements of different sense, clockwise, counterclockwise. Uh, so that's why we can just use the arrow. But you will see mostly we will use the sign. Okay, so what is this distance D? This distance D. The distance D is basically this 4 meter. 4 meter is from here to here, and then add this distance as well, which we will get from this triangle right here. From this triangle, diagonal is 2 meter, angle is 30. So what is the base? It is 2 cosine of 30. So this total distance is our moment arm, which is what? Which is simply 4 meter plus 2 cosine of 30. So the basic formula again we shall apply. The force into the perpendicular distance or the moment arm, and it will give you the moment 2292.82 Newton meter. Okay, or this is in Newton meter. You can convert this Newton into kilonewton just by dividing this number by 1000. So when you divide this by 1000, it will get converted from Newton to kilonewton. And when you do that, what you will get? You will get 2.29 kilonewton meter. And look at the sense. Is it clockwise or counterclockwise? Uh, if it's okay, you see, look at the arrow. The arrow is force. The arrow of the force is downwards. So what this force is trying to do? This force is trying to rotate like this about point O. About this point O, force is trying to rotate like this, and it is clockwise. Okay, so right here you see clockwise. Uh, I have a question here from Usama. Sir, why we not take okay your distance you sent why we not take the total distance in previous example? Uh, Total distance. Look, remember, we have to take the perpendicular distance. That's the basic thing. So it's not about total distance or partial distance. Asad, I see that. Asad, please, uh, by mistake, I think your cursor is drawing lines. So maybe not use the cursor. Okay, just a minute. Someone named Asad. His cursor is uh, drawing lines. So please make sure that you are not touching your mouse. There is a way I can control that, but okay, let's not touch your mouse. Otherwise, it starts misbehaving. So remember, it's not about total distance or partial distance. It's about perpendicular distance. Okay. So if you keep that thing in mind, you will not get confused. So we need perpendicular distance from the point about which you want to calculate the moment and the line of action of the force. Perpendicular distance. So it can be anything, uh, but don't worry whether we are taking I think you may be referring to this 3 meter that where we have not used 3 meter. We have not used this 3 meter because it is not the perpendicular distance. Perpendicular distance is from the line of action of the force to the point O, and right here you see this is perpendicular. So we need this distance. This is our D. We have to figure out how we can find this D. Okay, and we figured out that this D can be found by using this triangle. Okay, so you have to figure out sometime. Okay, now moving to the last problem, uh, which is right here, this one. Okay, here again, same question. Somewhere here is point O, and here is a 7 Newton force. Um, Again, this meeting will finish in 10 minutes, and after that, I will send another link. Okay, so just a minute, let me cancel this. Uh, okay, so you see, we have 7 kilonewton, and here is point O. We need to find the moment because of the 7 kilonewton about point O. Again, the same thing. What's the same thing is extend the line of action and try to find the perpendicular distance between the line of action, the force, and point O. You see, this perpendicular distance. So distance is always going to be perpendicular from the line of action of the force. Now, how we can find this distance? Very easy. You see that this distance is given as 4 meter. So from 4 meter, if I subtract this distance, which is actually given right here, it's written here 1 meter. So if I subtract 1 meter from 4 meter, I will get this distance. You see, this right here, 4 meter minus 1 meter is this distance. Okay, so 7 into 3 meter, you get a moment of 21 Newton meter. And again, you can tell uh, that it's clockwise or counterclockwise. Very easily you can tell. And that again from the line of action. Uh, this is the line of action of the force. Force is a sliding vector. You can show the arrow like this. Okay. Now see what this force is trying to do about point O. This force is trying to rotate like this. Okay. Which is what? Which is counterclockwise. Counterclockwise. So you see here we have shown counterclockwise arrow. Okay. So this is how we calculate the moment about force. So in all of these examples, 5 examples, we had uh, only one force. Okay, because we are just beginning this. You may have multiple forces, and we'll see how we deal with the multiple forces. And before that, let me see if I can answer the questions asked in the chat. The question is, it means it is not compulsory to D to pass through the object. Uh, compulsory to D passes through the object. What I understand is uh, pass through the object. What does that mean? It means it is not compulsory to D. Yeah, I think grammatically the sentence is not making sense to me. Maybe you can rewrite it. The other question is, sir, in this example, why we use cos angle? Look, this cos angle, we needed this distance, horizontal distance, okay, to reach to point O. 4 meter was given, and the remaining distance was this one. So you can apply cosine in this triangle. You know, this hypotenuse is given, angle is given. If we want to determine the base, what will that be? Hypotenuse into cosine of the angle. So that's why we use the cosine of the angle. Okay, because we need the base. Okay, that's fine. So why we are not using sine angle? Sine angle, if we use sine angle, it will give us the vertical distance. We don't need the vertical distance. We needed this horizontal distance. Okay, and this was part of the horizontal distance. Okay, Ahmad Roy, because I'm saying we need perpendicular distance, not total. Yes, of course, you need perpendicular distance, not total distance. You have to see from the line of action of the force to the point about which you want to determine the moment, what is the perpendicular distance? You have to find it, you have to look for it from the data, how to get that. It may not be directly given. You have to use trigonometry sometime addition, subtraction, something you have to do in order to find out that distance. Okay. But without finding out that distance, you cannot actually determine the moment. Okay. This problem, I hope we can finish this before this session ends. The difference between this problem and the previous one is that here you have multiple forces, multiple forces. Before we had only one force. The question is determine the resultant, right? It says resultant moment, okay? Because there are multiple forces. Resultant moment of 4 forces acting on the rod about point O. Here is point O, about which we want to find out the moment because of this 50, because of this 60, because of this 20, and because of this 40. Okay, so there are 4 forces, and some of them would produce clockwise movement, some of them would produce counterclockwise movement. Okay, um, and um, some of them we directly have the distance, and others we may not have the distance. We have to figure out what is the distance. Okay, so this is a good example to you know consider to solving understanding several cases in the same problem. But before I do that, I will stop this session and start a new one. So give me 5 minutes. And because the time remaining is only 3 minutes, so I don't want to, interrupt during the solution. So let's create a new session and then be back. Before I do that, Ahmad is asking here, we also use the free body diagram. You may use it, but these are actually very simple problems. So you don't have to redraw a simple, it's already very simple. So you don't need the free body diagram here. Okay. For a little bit more complicated, we'll draw the simpler diagrams. Okay, so I'm stopping this. And, please wait for the next one. Thank you. Okay, folks, let's get started. So you can see on the slides. Mhm. Okay, so you can see in this problem, we have four forces, 50, 60, 20, and 40. Okay, the question is we have to determine the resultant moment because of these forces about point O. Okay, about this point. Now, some of them would be producing clockwise movement, others will be producing counterclockwise movement. So in this problem, we shall consider counterclockwise as positive, which means clockwise as negative. So one by one, we will see what movement each force is producing and whether it's clockwise or counterclockwise. And then we algebraically sum all of them. Let's start with the simple one, which is 50. So look at this 50. If you look at the line of action of 50, it is downwards. So from this line of action and from point O, this is the perpendicular distance. See, perpendicular distance. And luckily, it's directly given as 2 meter. So we don't have to make any computation. We simply multiply 50 with this 2 meter and get its moment. You see here, we multiply 50 with 2 meter and that is the moment because of this 50. Now also see whether it is clockwise or counterclockwise based on the direction. You see the direction is downwards. So that downward direction tells us that it is producing a movement like this. Okay, this is clockwise. Okay, about point O. This is trying to produce a clockwise movement about point O. So mainly it's the direction that will tell you what sense of movement is being produced. So if it is clockwise, you have to place a negative sign. Okay. Okay. So this is the first one with a negative sign. And then let me clear this out. Okay. Now let's talk about this 60. Look at the line of action of the force. If I extend the line of action of the force, you will see that the line of action of the force will pass through point O. Okay, it's passing through point O. If it is passing through point O, it means there is no perpendicular distance. Okay, so if the line of action of the force passes through the point about which we want to calculate the moment, it means there is no perpendicular distance, no moment arm, I would say, and d is equal to 0. This is an important information because some forces you will see in problems will pass through the point, and you don't have to take any moment for those forces. So you will simply multiply 60 with a 0. There is no moment. So I repeat myself, if the line of action of the force pass through the point about which you want to calculate the moment, then the moment will be zero because the moment arm will be equal to zero. Okay, so this is the second one, uh, 60 Newton. Let's look at the third one. Third one is this 20 right here, 20. Now, same thing, extend the line of action of the force, okay, and try to find the perpendicular distance from point O, this perpendicular distance from point O. Okay. Now this perpendicular distance is not directly given. Okay. But there is some other information which is given and we can use that information. Look, I will make a triangle and that triangle will help us in finding out this distance. You see, this triangle. This is the right angle triangle. And if you know, focus a little bit, you will find that this perpendicular of the triangle is same as the perpendicular distance which we need. Okay, so it becomes very easy. The hypotenuse of the triangle is 3 meter and the angle with the base is 30 degree. So you can easily find this perpendicular distance. You can easily find the perpendicular distance. And how you will do that? This perpendicular distance will be equal to what? It will be equal to this 3 sine of 30 degree. 3 is hypotenuse. Okay. Angle is 30 degree. Right here, angle is 30 degree. So the vertical distance or perpendicular is 3 sine of 30 degree. And that perpendicular distance is same as the moment arm which we need. So we will simply multiply this 20 with its moment arm and you will get the moment arm as this. Okay. So 20 into 3 sine of 30 is the moment produced by this 20 about point O. Okay. So you see that you have to do some working before you can actually find the moment produced by a force. Now we have to see whether it is clockwise or counterclockwise. Very simple. Look, uh, this is the line of action of the force. This is the perpendicular distance, and the direction of the force is like this. So if that's the scenario, follow the direction, and you will see the moment produced about point O is counterclockwise. Okay. This is counterclockwise. So if it is counterclockwise, our counterclockwise is positive. So we have used a positive sign. Okay. Now let's do the last one. The last one is 40 Newton. This 40 Newton. Okay. Now 40 Newton, again, 40 Newton is here, point O is here, far away from each other. Do the same thing. Extend the line of action of the force like this and find the perpendicular distance from point O. This distance. The angle is 90 degree. So this is our D. We have to figure out how we can calculate this D. Okay. Okay. So how we can find this D? Again, we will have to use some existing distances and some maybe from the triangle or something. Look, part of it is given here 2 meter, 2 meter, 4 meter, up to here is 4 meter. Then this distance we have to figure out. If we can find this distance, we can add it in 4 meter and that will be our moment arm. Okay. And this distance, we can use the same triangle as we used before. You see, uh, let me make that triangle. So if I make this right angle triangle again, this time, you see, I make this right angle triangle. I am talking about the base of this triangle, this base of the triangle. So on this triangle, if I simply do this, 3 meter into cosine of 30 degree, then I will get this distance. So my total movement arm, right, of this distance, this is my movement arm, that will be equal to 2 meter plus 2 meter plus this distance, which is 30 cos 3 cos of 3 cosine of 30 degree. You see here, I'm multiplying this 40. This 40 is multiplied with the moment arm. And this moment arm is basically this one, this distance, which is 4 meter. 4 meter is this 4 meter plus 3 cosine of 30 degree. And 3 cosine of 30 degree is what? 3 cosine of 30 degree is this distance. So together, 4 plus 3 cosine of 30 degree is the moment arm of the 40 Newton force with respect to point. Okay. Uh, okay. Zainul Abidin, I guess. I think your mouse is drawing lines. Okay. So now look at the sense, clockwise or counterclockwise. Again, you see, uh, this is the line of action. This is the movement arm, and this downward is the mm, this this downward is the direction. So what this downward force is trying to do? This downward force is trying to reduce this kind of rotation about point O. Okay, the point O taken as a center of the circle. So this is clockwise. If this is clockwise, then the sign for this is negative. Okay, so you simply add all these algebraically, add all of these algebraically, and you will see that you will get an answer of minus 334 Newton meter. So if you got a negative sign, it means according to your sign convention, clockwise, counterclockwise positive means clockwise was negative, so it is a clockwise movement. So either you can write it minus 334 or you can write 334 and make a small clockwise arrow. We shall actually write the sign in future when we shall do the movements. We will write the signs. Okay. Okay, I have a question from Dayan Khan. Sir, can we also assume clockwise to be positive? Yes, definitely, we can assume clockwise positive. There is no harm at all. Okay, sign convention just help us differentiate between two different types of movements. Okay, so it separates the clockwise and counterclockwise. There is no compulsion that we will have to take clockwise positive or counterclockwise positive. It's just that you decide once and then keep following it. Okay, you will see that somewhere we may use clockwise positives. So your knowledge or your understanding should be independent of the sign. Okay, but I think mostly the book will use counterclockwise positive. But again, I would say do not get trapped in the sign convention. Focus on the concept. Okay, so this first finishes this problem. Anybody has any other question related to the problem? Okay, there's no problem, no question. Then I will move to the next slide. Do we have the CR here? CR Zen is the CR or someone else?
Yes, sir, I am here.
Okay. Can you please mark their attendance? Because
सर कोडिंग कर
I
लेता
know,
हूँ जितने भी.
no, I know that how many students are here. I mean, counting is not. I need
ओके सर.
who is here. I mean, attendance. I know that there are 35 participants, 34 students, and one is myself. So I just need to know. You can take a screenshot. Can you see the participants, the name of the participants?
Yes, sir.
Okay, then you can just take a screenshot and maybe you can later on give it to me. I
ओके
mean,
सर.
I will need the roll numbers, of course, because attendance. Have you received roll numbers or no?
मिल गए हैं.
Okay, so first thing is that you write the names. I mean, take a screenshot, and then if you don't know the roll numbers, maybe in the class later on we can ask for the roll numbers. Okay,
ओके
but at
सर.
least
ओके सर.
take the screenshots.
ओके सर.
Okay, thank you. Um, okay, so moving forward, next slide. Next slide is principle of movement. Okay, principle of movement is same. You have performed the experiment in the lab related to the principle of movement. And I will quickly read that. Um, a concept often used in mechanics is the principle of movement, which is sometimes referred to as Varignon's theorem, since it was originally developed by the French mathematician uh, Pierre Varignon, 1654-1702. So it's a couple of 100 years ago. Uh, so what is principle of movement? It states that the movement of a force about a point is equal to the sum of the movement of its component of the force about the same point. Okay, I think it's another version of principle of movement. In the lab, you actually said that sum of the clockwise movement is equal to the sum of counterclockwise movement. Okay, here is a different version. What is that version is? It says that moment of a force about a point is equal to the sum of the moments of the component of the force about that point. Means you have a force. You calculate the moment of that force about the point. Okay. Now, that moment, save that number. Now, the same force you resolve into components. And from those components, you calculate the resultant moment or the total moment. You will see that the two moments are equal. Okay, let me show you from here. Uh, you see here, we have a force F. Using this force F, if you calculate the moment about point O, you see how you do that. Extend the line of action of the force and get the perpendicular distance D and calculate the moment. Simply multiply the force with the perpendicular distance. Okay, and that is m equals to F into D. This is the moment because of the force itself. Then you do this. You resolve this force into two components. What components? You resolve the force into Fx and Fy. Then you calculate the moment because of Fx and Fy about point O. Okay, how you do that? Look, because of Fx, extend the line of action and get this perpendicular distance. This perpendicular distance is equal to what? It's equal to y. So the moment is simply Fx into y. You see, Fx into y. Then due to Fy, extend the line of action of the force, and you see, this is the moment on perpendicular distance. This perpendicular distance is actually given here, x. So simply multiply Fy with the x, Fy into x. So this and Fy into x is, you see here, I think here the author has used clockwise positive. Very strange. Um, because it's the same book and I don't know why he changed the sign convention. But anyhow, fx is producing clockwise movement about point O. and Fy is producing counterclockwise movement about 0.0. So he has taken clockwise as positive, clockwise he has taken as positive, and he has used counterclockwise negative. So you see, very quickly we found an example where the clockwise is positive and counterclockwise negative. Anyhow, this they together are producing the MO. Together they are producing MO about 0.0. So this is the moment because of the components, and F into D is the moment because of the original force. So Vrignan theorem is that these two moments are equal. Okay, so moment produced by the force and its component about the same point will be equal. Okay, this is the Vregnan's theorem. Okay, um, Ahmed is asking point means the moment axis. Yes, point actually, when we say point, this actually means that the axis which is passing through this point O. So there is an axis perpendicular to the plane of the slides which is passing through point O. The moment is about that axis. But this is a common practice that instead of saying movement about an axis, we say movement about the point. Okay. So it's easier to say. That's the only thing. Okay. If I move forward, just one more slides and then we will close the class. This is this example is about the Vregnan's theorem, moment of the force and the moment of the components of that force. That we shall explain here. It says that for the force F, this force F, which is 400 Newton, at the end of the angle bracket, this is the angle bracket right here, angle bracket, just like a set square. Angle bracket determine the moment of the force about point O. This is the point O. Okay. So what we shall do is, look, if I ask you to get this moment according to our basic formula, force into distance, then what you will do? You will say, okay, let's extend the line of action of this force. And from the line of action of this force, get the perpendicular distance, this perpendicular distance d. This is the perpendicular distance d, and then multiply F with d, and this will give you the moment produced by F about point O. Okay, conceptually it's okay, but the challenge is that D is very difficult to find. We don't have, in the dimensions which are given, this 0.2 meter or 0.4 meter. Based on this, we cannot find D. So finding D becomes a challenge. Okay. Otherwise, simply multiply F with D and you get the answer. Now, how we solve this problem? We will use Wegener's theorem. We'll say, okay, we cannot find the moment directly by F into D, but we can do is we can resolve our force 400 Newton into a horizontal component and vertical component. And then using those horizontal and vertical component, we can find the moment about point O. And if you recall chapter number 2, how we resolved the forces into component, it was F cosine of theta and F sine of theta. And F is in 400 Newton is in fourth quadrant. Okay, it's in fourth quadrant. So we will use the same concept. But what book has done is book has used angle with the vertical, and I always said that we want to use the angle with the horizontal. So all the calculations given here are with respect to the angle with the vertical. But angle, when we do the angle with the vertical, then x component becomes sine of theta and y component becomes cosine of theta. But I never want to do that because it will only create confusion. So what I do is I always use the angle with horizontal. So it means that the angle, um, let's resolve this one, this one, two components, and I want to use this angle, which is 60 degree. Okay, then if I use this angle 60 degree, then my horizontal component will become what? It will become f cosine of 60 degree, and the vertical component will become what? It will become 400 into sine of 60 degree. Okay, so let's see how we can find the moment. Okay, this one, let me write it down. This is 400 into uh, cosine, please, this handwriting is not good. This is 400 cosine of 60, and this is 400 sine of 60. Sine of, it's very hard to write with this, and I don't have a mouse actually. Maybe with the mouse it's easier. Okay, so this is 400 sine of 60 degree. Now you have to find out for each of them the moment arm. The moment arm is what? Same thing for the moment arm as we did before. That, for example, if I want to do it with 400 cosine of 60, extend the line of action of the force, and from point O, find the perpendicular distance like this. Okay, so this is our perpendicular distance. And can anybody tell me, do we have this perpendicular distance given in the problem? Anybody? Do we have this perpendicular distance somewhere given in the problem? Please write down in the comments. I don't. Yes, it's 0.2 meter. Correct. It's given here, 0.2 meter. So we simply multiply 400 cosine of 60 with 0.2 meter, and uh, this will give us the moment. And you see here, because book has used angle with the vertical, so the author has, multiplied the x component with 0.2 meter. Okay. Only difference I have is that instead of sine 60, I do not have sine 60. I have what? I have cos 60. Maybe I will fix this before I give you the slides. So this is the horizontal component, and then the vertical component. Vertical component, you see, sine 400 sine of 60, do what? Extend the line of action, and from point O, try to find out the perpendicular distance, this perpendicular distance right here. So this is our perpendicular distance. So is it given? Can anybody tell me? Is it given in the problem somewhere? The perpendicular distance? 0.4 meter. Yes, that's correct. It's given right here, 0.4 meter. So you simply multiply 400 sine of 60 with 0.4 meter, and this will give you the moment. You see here, 400, yes, he has used cosine of 30 and I have used sine of 60. So the vertical component 400 multiplied with the 0.4 meter moment arm, and with this, ultimately, you will see that your answer will remain unchanged. The uh, answer will be ultimately same as the book. Whether you use 60 or you use 30, minus 98.6 Newton meter. Minus means that it is clockwise. Here we have used uh, counterclockwise, as positive. Okay, so either you use minus sign or you use a small arrow showing that it is a clockwise moment. Okay, so that finishes this problem. I will stop here today, and next time when we come back, we will start learning about the couple movement of the couple. Okay, what's the question? As we said, quadrant 4 है, so fy के साथ negative आया है. Look, here we are not using the sign of the force. We are not saying that the force is downward, force is rightward, force is leftwards. No, we are just looking at the sense of the movement they are producing. For example, this 400 sine of 60 is producing, you see, like this. It's producing a clockwise movement. Okay, 400 sine. The vertical component is producing clockwise movement about point O. That's why it has a negative sign. So the sign here is not when you are calculating the moment, sign depends on clockwise and counterclockwise. It does not depend upon downwards, leftwards, rightwards, upwards. Okay, that we use when we deal with the forces, deal with the resultant, calculate the resultant of the forces or apply the equation equilibrium. But when we are calculating the moment, we only see whether the force is producing clockwise movement or clockwise, counterclockwise. A force may be in the first quadrant, but still it may have a negative sign with the moment because it is producing the clockwise movement. So remember this thing that when we are calculating the moment, the sign comes from the sense of the moment and not the direction of the force. So is it clear or no? Or anybody has any other question? Okay, if there is no question, I will close the session and I will share the slides with you later on. Thank you very much, everyone. And Zen, have you taken the screenshot for the attendance?
यस
Because
सर मैंने ले
after
लिया वो मैं लिख के आपको दे दूंगा फिर.
okay, wonderful, wonderful. Okay, everybody, thank you very much to have a nice day.